In chemical reactions, then we're taking these molecules, we're breaking them apart, and all of these things that make up that entropy calculation. And we're saying, how does it change? It's a state function, so it doesn't matter like all of the steps in between. That'll be relevant later. But really, this calculation, and we're going to see similar one, or actually, you've already seen one for enthalpy, for delta H, right? You take the heat of the products minus the heat of the reactants and see if it's overall exothermic or endothermic. We'll do it for entropy, so the randomness or the chaos, and we'll do it for Gibbs free energy. And in all of these cases, all we're really trying to say is, does it get bigger or does it get smaller, and by how much? So I think it helps to keep in mind with these kinds of calculations, which, just to walk through, right, this is the sum of, it's actually sum product, right? So you take all of the products, take their standard entropy, multiply it by whatever its coefficient is in the balanced chemical equation, and we would add all of those together, and then we do the same for the reactants, and then we subtract them. And all this is really doing is saying, what is the entropy of my products? What is the entropy of my reactants? And how are they different? This is the math way of saying that. So I think it helps to keep in mind almost like a reaction energy diagram, which they'll become reaction energy diagrams. Right, so if we have, really the x-axis is just reaction coordinate. And this is, in this case, we're going to do it for delta S. What we want to do is calculate what is it for my reactants. So it might be this, and then maybe it's up here for the products. What is it for my products? So we're calculating those two levels, and then we compare them by subtracting them. And just like calculating, it's called the law of mass action, but when you're calculating a K value, it's always products over reactants. This is always products minus reactants. And so it's kind of like saying, where am I going? Where did I start from? What's the difference in between? So this would be our sum of NPS standard for the reactants. This would be the sum of NP standard enthalpy of the products, and then the difference between these is delta S for that reaction. And so in a sense, we're taking, again, all of these. So these standard enthalpies, or standard entropies, represent sort of the sum total of all of the I guess we can call it entropic factors. That's a cool sciencey word. Entropic factors, whether it's a solid, liquid, gas, molecular complexity, molar mass, taking all of these things, whether it's dissolved, and it's like, that is the defined standard for this thing. And now if I put that in as a product or a reactant, I can say, okay, all of these reactants turn into all of those products. Do I have more or less entropy? So it looks like a big fancy equation, but it's just a mathematical way of saying what's the difference between where I start and where I end. And I know I've said that like 5 or 6 times now, but I think it's really important to keep that in mind, because keeping that in mind can guide the way that you write these equations. Like, we know that we're just doing this comparison of products and reactants, then you don't need to memorize an equation. I just calculate for my products, I calculate for my reactants, and I subtract. And there's a direction to this, right? So the negative tells me which direction I'm going, in that I'm going from reactants, I'm going to products. So if my products are bigger than my reactants, and actually, let's just calculate this here. So I'm going to set this up differently than the book does. I'm going to write products up there, and I'm going to write reactants down here. And we're not going to subtract, or no, sorry, we're not going to divide, but I think it's a nice parallel with, and really for the same reasons that for law of mass action, calculating equilibrium constants, it's products over reactants, it's products minus reactants. That order matters because there's a direction to a direction to our reactions. So on a table, you'll be given values of, bless you, values of entropy. And so I'm just going to take 2 times whatever the value is for water. And with water especially, always make sure that you've got the right state, because you'll probably have solid, liquid, and gas on the chart, which is why state symbols are important to include in chemical equations. So this is for the gas. We've only got the one for gas. And I'm going to add that to 2 times SO2, which is 248.2. And then I'll do the same for my reactants. So 2 times 205.8 plus 2 times, or sorry, not 2, 3 times 205.2. And those are all joules per mole Kelvin. So this is 874 joules per mole Kelvin. Oh, this would be a good exam question. Come back to that in a second. Ask you that question. Right, so the first part of this equation is really just to say all of my substances, all of my compounds have some inherent entropy in whatever form that they're in this chemical equation, and we've got those standard values. And so I'm adding up, my products have this total entropy of 874 joules per mole Kelvin. My reactants also had some standard entropy each. Multiply those by those coefficients, right? Because every O2 is going to be 205.2. So if I've got 3 O2s, then 3 times that. Add all of those up, now I get some new entropy. And then the last thing that we want to know is, does my entropy decrease or increase going from reactants to products? So does it increase or does it decrease? Careful. Decreases. Yeah, I wrote products on top and I wrote reactants on the bottom, but yeah. Mostly just to draw that parallel with K values, right? When you calculate K, it's products divided by reactants. This is products minus reactants. And actually, so when we set this up the same way, we subtract. And entropy decreases. I know what the entropy of my products is. I know what the entropy of my reactants is. I can see that my products are less than my reactants. So entropy decreased one way or another. And actually, we could maybe say how it decreased. So 874 minus 1027.2. This is negative 153.2 joules per mole Kelvin. So what's one reason that entropy decreases here? Or at least part of it. We have a decrease in the moles of gas. So unless something else changes, like one of these molecules gets a lot of molecular complexity or something, we would expect this to decrease. And so our numbers match that expectation. Now for the good test question that I just thought of. Entropy values, standard entropies, are always positive. Why is standard entropy always positive? So not the delta. Well, I mean, the delta is negative here, right? This is the delta S. But this is not a change maybe in the standard sense, right? That's just hydrogen sulfide has 205.8 joules per mole Kelvin of entropy. Molecules are always moving. Yeah, yeah. So you got there a little bit indirectly, but maybe everybody was thinking this because there's no duh, but right, the standard entropy is always positive because we're comparing it to absolute zero. We're comparing it to zero entropy. That's not the case with enthalpy, delta H. We can have negative enthalpies because it's calculated heats of formation. But for entropy, why do they make these words so similar? For entropy, delta S, or sorry, S0, right, S naught, it's always going to be positive because we're comparing it to a perfect crystal at 0 Kelvin. And so we can't have negative Kelvin, can't have negative absolute temperatures. It's like, okay. So right, the importance of writing it out this way is that we're just sort of comparing. And actually, if we take these numbers now and we move up back up to here, we can plug these numbers in and we could say 874 is my products, which actually change this, right? So what we're saying is that my product entropy ends lower, 874, where this was, what, 1027? Joules per mole Kelvin. So we're saying my reaction starts at one point, ends at a different point. The difference between them is the delta S. And since we're just like, you don't have to do any like complex calculation to get those entropies, just look them up on a table. All right, so delta G. So we've had, you guys in Chem 1 talked about standard enthalpies, so delta H naught for a reaction. But if we know delta H naught, if we have these standard enthalpies and we have standard entropies, we can use those to calculate a standard free energy. And this is the same equation for before, delta H minus T delta S. We can also calculate directly from standard entropy or standard free energy of formation values, which we'll see. And then we can also add equations together, just like you did with enthalpy, because it doesn't matter if it happens in one step or in multiple steps. Wherever you start and wherever you end determines the change in free energy overall, determines the change in entropy overall, determines the change in enthalpy overall. So like all three of these are state functions and are very, very parallel to each other. So this same equation that we can use for entropy, we can use it for enthalpy. And then if we calculate the delta S and the delta H standard of a reaction, then we can use those to calculate delta G. Now, most of the time, well, only valid at like 25 degrees C. In the textbook, it explains that like the values don't change that much around 25 degrees C. So there's a range that you can get really good approximate values for. But strictly, these would only be at 25 degrees Celsius. All right, I went and I grabbed some tables values because they weren't in here. If we want to calculate delta G, and all we had were standard enthalpies and standard entropies, we could do that. And again, it's going to be products minus reactants. So NO2, if I want to calculate delta H of the reaction, then that's going to be nitrogen dioxide, 33.2 minus 91.3, and then technically it's plus 1/2 times 0. I do recommend, whenever you're doing these, if you set it up this way especially, put this parentheses around your reactants. Like the whole reactant side is being subtracted. So you want to calculate all of these first and then subtract, not just make the first one negative, especially on your calculator, because that's exactly what your calculator will do. So okay, delta H of the reaction then is negative 58.1. And then we can do this for delta S also. And this is going to be 240.1 minus 210.8 plus 1/2 times 205.2. Oh, which of course I already calculated. And negative 73.3 joules per mole Kelvin. And then delta G, Gibbs free energy of the reaction. It's going to be my delta H. And let's do this in, because delta S is in joules, because delta S entropy values typically small. So joules makes more sense. But when we combine these together, we need to put them into the same units. And I think it's going to be nicer to do this in kilojoules than in joules. And delta G, I think, is typically kilojoules. So 58.1 is my delta H minus T, which is 298, times delta S, which is negative 0.073.3. I don't know why I put 2 decimals in there. So delta G of the reaction is negative 79.9 kilojoules. So is this spontaneous? So the way to think about delta G and whether or not something is going to be spontaneous or not at this temperature, again, we can do like a reaction energy diagram. But with delta G this time. And even though we don't know what like the delta G is of my reactants and the delta G of my products, what we do know is that this changes by some amount and it changes by a negative amount. So are my products going to be higher or lower than the reactants? Lower. So I'm just going to put this here. And because this is all relative anyway, I'm just going to draw this down here. So, right, this is the reactants, products, and then whatever this distance is my delta G, which is negative 79.9 kilojoules. But importantly, it's downhill. From left to right, we go from high to low. So if you remember that delta G is essentially, well, I'm going to say pretty much chemical potential. This is why the analogy with mechanical potential energy is important. Things roll downhill, things fall downhill, things go from higher to lower. And it is the same with delta G. If delta G is negative, it means we're going from higher free energy to lower free energy, which means we're moving downhill, which means that this is spontaneous. Maybe I should have drawn this with... So in our reaction diagram, whatever happens in the middle, we can sort of imagine, right, like we're moving downhill. In terms of chemical potential energy, we are reducing that chemical potential energy, which is spontaneous. I'll say we, I'll say the reaction. And this is what's so great about delta G. This is what's so great about Gibbs free energy, is that it tells us which reactions will happen. It doesn't say how fast, it doesn't say how far that they'll go, but it does tell us that that reaction under standard conditions, are we gonna get to that slide today? I think we'll get to the slide today. Under standard conditions is spontaneous. And so this is the guiding principle of like, well, why did chemists even want to figure this stuff out? Because with this, we can tell if a reaction is going to be spontaneous or not. I didn't get a chance to like write it up in the slides, but there's a great example in the textbook about generating hydrogen gas. The generation of hydrogen gas is a non-spontaneous process, a very non-spontaneous process. But if you can combine that reaction with another reaction that is spontaneous, in a sense, more spontaneous than generating hydrogen is non-spontaneous, then you can make your non-spontaneous reaction happen by coupling it with a spontaneous one, because the overall change in energy then ends up being downhill. I think it would be kind of like if you're starting with a ball on a hill and my first reaction would be rolling down this hill. You're going to pick up a bunch of momentum. And this is just a rough analogy, but when you get to the bottom of the hill, that's my first reaction, but now I've got sort of enough leftover energy that I can get over this smaller hill. Actually, it wouldn't be like that. It would be like this. And so there's enough energy left over that I can come back up the hill on the other side. So we can couple a spontaneous with a non-spontaneous. We get a big negative delta G coupled with a smaller positive delta G. And at least under, again, standard conditions, this is true. Any reactions that you couple together, you don't need to know anything else about it. If you can put those reactions together under standard conditions, the reaction will happen. Okay, so the much easier way to do this is to actually just start with standard values for the reactions. Oh, right. We got different temperature now. So we calculated already our standard values, and we can sort of use this to make predictions about delta G. It's not going to be perfectly accurate. as we get away from that standard temperature, but this is a small enough change that it won't matter enough. So here we're calculating delta G. Standard conditions, even though our temperature is non-standard. And there's going to be negative 58.1 kilojoules minus T, which is 273 minus 55. So it's 218 times, oh, got to convert this to kilojoules. So this is still negative 42.1 kilojoules. So is this spontaneous? Yeah, still spontaneous, even at this lower temperature. Again, delta G is just telling us, are we going downhill or uphill? Negative means we're going downhill. Means that the products are lower than the reactants. So we're going downhill, so it's still spontaneous. Now, did it become less spontaneous? If we look at what our value was before it was negative 79.9. If I'm going downhill, now this is less downhill. So if I continue to decrease the temperature, there will be a temperature at which this becomes non-spontaneous. And if you want to solve for the temperature where something is non-spontaneous, set delta G delta G is 0, that's the inflection point. Right? Because as soon as the temperature drops more than whatever it is when delta G is 0, then delta G will become positive. And this changes depending on whether or not my entropy or my entropy and my enthalpy have positive or negative values. Because there are certain conditions, I think when one's positive and the other's negative, then it's always spontaneous or always non-spontaneous. Here at low temperatures, so both negative, at low temperatures it'll flip. They're both positive. At high temperatures it'll flip. All right, so like I was saying, the same thing that we did with delta S and delta H, we can do with delta G using free energies of formation. So again, we have to have some sort of defined standard state. And our defined standard state is forming something from 1 mole of a compound in its standard state from its constituent elements in their standard states. And we define the free energy of formation of pure elements in their standard states is 0. Typically, this is going to be whatever state it's in at 25 degrees C. So if we're thinking about oxygen gas, then O2 as a gas, that would be its standard state. So in that state, its Gibbs free energy would be 0. Maybe look at some other values. But again, same equation, right? Products minus reactants. And this products minus reactants equation is, again, just like calculate for the products, calculate for the reactants. Does it go down? Does it go up? And these can be negative. So we want to use standard free energies of formation to figure out if it's going to be spontaneous at standard conditions. So we need to calculate free energy of, actually no, we've got things that are on here, so we don't actually need to calculate all that much. But again, I want to set this up as products, and then it's going to be products minus reactants. So for my products, it's going to be 2 times CO2. So CO2 is negative 394.4. Plus N2, and N2, it's like I was saying, nitrogen at 25 degrees C is most often going to be N2 as a gas, so that's its standard state. So that's plus 0. And then for the reactants, it's going to be 2 times negative 137.2. Common mistake is just you got to pay attention to the small details, right? CO versus CO2 is going to have a different delta G, but it's easy to look quickly at the chart and grab the wrong one. And we add that to nitrogen monoxide. We're not going to get to that other slide today. 2 times. And again, what we're doing here is we're calculating the free energy of the products and comparing it to the free energy of the reactants, which when you just write it out as the whole equation kind of gets hidden, but really all we're doing is comparing those two things. 394.4 times 2. So this is negative 788.8 times negative 137.2 plus 2 times 87.6, negative 99.2. But I'm subtracting these. But negative products is a lot bigger than, wait. Oh yeah, because it's a positive 87. So like these free energies end up canceling each other out a little bit before even I subtract. So negative 78 minus a negative 99 is negative 689.6 kilojoules, and that's my delta G for that reaction. So is it spontaneous? Yeah. Is the reaction moving downhill? If you think about if I'm starting at negative 99 and I go to negative 788, then I'm getting more negative. It's still downhill. Cool. So the real power of this comes when you try to like make up other equations or try to get, again, take a non-spontaneous reaction and make it spontaneous. Actually, wait, what was this? Oh, okay. This is fine too. It's like we can take multiple reactions just like we did with Hess's law. It applies also to free energy. And it's the same rules. So like if an chemical equation is multiplied by a factor, then we multiply delta G of that reaction. If it's reversed, then delta G changes signs, which makes sense because if I'm comparing products to reactants, if I'm going downhill in one direction, I'm going to be going uphill in the other direction. Which is why it's impossible to walk to school uphill both ways. It's got to be uphill in one direction, downhill in the other, unless you're in an MC Escher painting. And then if a chemical equation can be expressed as a series of steps, then we just add up all of those steps. So here we've got delta G's for a bunch of different reactions, and we have to combine these together to make the equation that we want, or the reaction that we want overall. So we want to know, is this overall reaction going to be spontaneous? And we've got delta G's for all of these parts. Is there an easier way to do this? Well, so the way I always approach these is I first look at all of my reactions that I'm going to be adding together, and I say, well, where is everything with respect to my final reaction? which is made more confusing because we've got so many, it's all nitrogens and oxygens, just different numbers. So like if I want dinitrogen monoxide in my reactants, then I want to make sure that dinitrogen monoxide is in my reactants. If I want nitrogen dioxide, needs to be a reactant. See, nitrogen dioxide here, not in the reactants. So I need to flip that equation. And how do I flip that equation? Flip the sign. So multiply that by a -1, at least for now. Let's see. What other things do we have to move around? Okay, so I got nitrogen monoxide. So there's a nitrogen monoxide there, there's a nitrogen monoxide there. So I do need, that doesn't change the fact that I need to flip the first one. So let's rewrite this. Equals positive 2 kilojoules because I rewrote it. So now we can get, not that, this. All right, so now I don't need that. Now we need everything to add up so that we get 3. This is a fun one.
You have to multiply the molar reaction by 2 and then divide the whole thing by 1. So you have to cancel out your 2 nitrogens.
Right now I'm gonna end up with
So you end up with
4. Oh,
the whole thing by 2 and you end up with 1, 1, and 3.
I mean, I believe what you're saying. You said multiply. Okay, that's what, that, yeah. Oh, you said multiply the top one by 2. Yeah, because that'll cancel out the nitrogens. And then that means my oxygens will be, oh, 2 on the left, 2 on the right. Those will cancel. Nitrogen cancels. Yeah, and then we'll get something that we probably need to divide by 2. Oh yeah, because it's going to be 6. So we could multiply by 2 or we could divide by a half. But this will cancel. These will cancel. And that'll leave me with 2N2O plus 2NO2 gives me 6NO. And then take this and divide by a half, which means that whatever this delta G of reaction is, 175.2 times 2 plus negative 207.4 plus a negative 207.4, I should have said out loud, plus 71.2. So for this, it's 214.2, but I need to divide by 2. And then this will be N2O plus NO2 is 3NO. Perfect. The key is to not get overwhelmed and just move one thing at a time. Make sure everything's on the same side. and then start canceling out. And like you could have done this a different way. Like instead of multiplying that 1 by 2, we could have divided the other 2 by 2, multiplied by half, and both would get us to the correct final answer. So we can add those up. So why free energy is free? Nothing's really free, but what's free about it is that it lets us calculate how much energy is lost to just the reaction happening and how much extra energy gets released into the environment in one form or another from that reaction. Because there are a lot of reactions, like burning gasoline is a reaction that goes downhill, it's spontaneous, and it generates a lot of extra energy on top of whatever needs to happen for that reaction to actually occur. Or taking carbon and hydrogen and combining them into methane, which has, well, a negative 74.6 kilojoule enthalpy. So we get this extra heat out. But some heat has to be lost to the surroundings, as is 24.1 kilojoules. Like we can't use all of that heat, and that's what the heat tax is. Because if we were to like throw all of this into delta G, delta G equals delta H minus T delta S. This T delta S is the entropy, like the entropy change, which is like the amount of heat that needs to be lost to the surroundings. Right, no, it's the H, it's delta H. One of these is the enthalpy that needs to be lost to the surroundings so that the entropy of the surroundings increases enough for the reaction to be spontaneous. So we're taking here two things, right? We take two things and we combine them into one thing, which is going to decrease the entropy of that system. So like in here, this is going to be a negative delta S. So outside, I need to be increasing the surrounding entropies by at least that amount. And the way we increase the surrounding energy is by, yeah, that's it. This 24.1 is the delta H. Because we got that from the amount of heat lost to the surroundings divided by the temperature of the surroundings. Because the entropy of the universe has to increase. That's the second law of thermodynamics, but it's of the universe. So some heat has to be just spread out. If we spread out that much heat, then the rest of the heat, in theory, can be used to do whatever work we want it to do. Now, the entropy here, or the amount of energy that we can get out as usable work, is a lot less than that in reality. So the amount, it's going to be less than delta G. Delta G is in theory how much we could use, but in reality ends up being a lot less because on top of the heat loss to the surroundings, we also just can't capture all of that energy. The only time that you can actually reach that theoretical limit is in a reversible reaction, but if you recall, reversible reactions only happen at like the very, very edge of being spontaneous or non-spontaneous, happening or not happening, going forwards or backwards. And so the slower a reaction goes, the more of the free energy you could use, in theory. But it's only at that limit. So like in this case, we have gas and we incrementally remove sand like 1 grain at a time, where the pressure is essentially always equal to the weight of the sand, and there's no friction between this like piston and the cylinder, and the temperature doesn't change. Then you could get more work out as this gas expands. But it just doesn't happen in real life. Because all of the energy is always lost along the way. Basically, everything's irreversible. So, oh yeah, we gotta get, man. All right, that's a good place to stop. we got to talk about this one. Should be non-standard conditions.